My name is Frédéric Gosselin, and I'm a professor of mechanical engineering at Polytechnique Montréal. This is the work of my former graduate student, Mouad Boudina, about the vibrations of soft corals. And so this is work that was done in collaboration with my colleague, Professor Stéphane Etienne, thanks to funding from NSERC and from the simulations-based engineering program at Polytechnique. And so, like all good work, this started on holiday. Basically, I was vacationing in Mexico and I went for a scuba dive. And what caught my attention was these vibrations that I could see at about 20, 30 feet deep of Antillogorgia bipinnata. So this bipinnate sea plume, which we see here under a gentle wave surge at the bottom of the ocean. So this is a video that was picked up from YouTube, which really illustrate the phenomenon well. And so basically what we see is that with the gentle wave surge at a low frequency, so that the waves pass by at less than a hertz, the entire colony sways with it. But the small branches, they vibrate at much higher frequency, around like 7 or 9 hertz. And so there's a bit of a disconnect between the low frequency swaying of the waves and the high frequency of the branches. So let's investigate it deeper. So basically, Antillogorgia bipinnata can be found around in the Caribbean, South Florida, around Mexico, and this soft coral is part of the subclass Octocoralia, and as its name indicates, it has polyps with 8 little tentacles. And so Octocoralia are animals, right? So they're these little polyps. They have tentacles, so they catch food that passes by and they eat it. And so soft corals are not plants, right? Even though I'm in the plant biomechanics session, but they kind of behave like plants. Like they're branching and they're anchored to the ground. So there are some similarities in their biomechanics. But what sets them apart is that they're passive suspension feeders. So what this means is they're passive in a sense that they wait for the currents to bring food particles in contact with them. And then the polyps just grab them as they pass by. And so, but they live off the food that they can catch in the nutrient poor ocean waters. And so this problem is similar to one which is found in terrestrial plants, that of pollination. And so Espinosa ran some computational fluid dynamics models to see how a fixed cylinder could capture particles that were advected by the flow. And then Crick and Ackerman pushed this idea further, simulating the advection of particles by a flow and how the motion of a collector could actually catch them. But they didn't look deeply at the basic fundamental parameters of how the vibrations would affect the particle capture. In the same research group, McComb and Ackerman did nice field experiments where they attached some seagrasses, some grasses, and some others that they left free to vibrate, and they found that the grasses that were free to vibrate would capture more pollen than those that were limited in their motion. So there's an important aspect, whether of pollination or food capture, that's related to cylinders catching things as they go by. So coming back to our problem here, looking at these vibrations, it raises two questions. So first, what's the origin of these vibrations on our soft coral? And what's their biological significance? So we'll try to bring answers to both these questions in this talk. So first, in terms of origin, we considered first turbulence buffeting. So basically, could eddies already present in the flow be responsible for these vibrations? But basically, the eddies in the ocean here are created mostly by the surface waves, and the surface waves are at a much lower frequency than those that are observed here, and because the branches are not always oscillating too, it just doesn't add up. The other mechanism possible would have been galloping, but these branches are almost circular and they have much more drag than they have lift. So we ran some computations, but there was just no way they would be prone to galloping. And so this left vortex-induced vibrations. And so we used the ImageJ, a free software image analysis software, to evaluate this video and others, and we found that we could estimate roughly the water flow speed by tracking some particles in the flow. We could measure very precisely the vibration frequencies of these of the branches. We could evaluate the branch diameters, and plugging this with seawater viscosity, we can estimate the Reynolds number to be around 200. And that's high enough for vortex shedding to occur behind a cylinder. I'll explain what that means in an instant. But more importantly, we could estimate the reduced velocity, which is the ratio of the free stream velocity divided by the vibrating frequency of these cylinders, or the branches in this case, and their diameter. And so when we take this ratio, we find that it's about 5 or 7. And this is a telltale sign that we're facing vortex-induced vibrations. So that got us very confident. So what are vortex-induced vibrations? So if you take any bluff body and put it in a flow at a Reynolds number high enough for inertia to be important, what you'll see is these, in the wake of the object, if you subject it to uniform flow, eddies will be shed with alternating eddies will be shed in the wake of the object, and with them will come a pressure fluctuation on our object or our cylinder. And so if this cylinder is spring mounted, for example, or if it's flexible like a cantilevered beam or a branch, then this pressure fluctuation can couple with the vibrations of the object and give rise to vibrations. And so we can illustrate this with a cartoon here. So basically, we have the vortex shedding frequency, which increases linearly with the flow speed. So the more you increase the flow speed, the faster these vortices are shed. And then you have the spring-mounted cylinder natural frequency, which is independent of the flow speed. And so when both of these frequencies match, we get what's called frequency lock-in. And so the shedding frequency will lock onto the natural frequency of the cylinder. And we'll observe large amplitude vibrations of the order of the cylinder diameter of the cylinder. So the cylinder will vibrate at large amplitude in that frequency lock-in range. And so in a nutshell, this is what vortex-induced vibrations are. And so to get a qualitative assessment of the possibility that we could be facing vortex-induced vibrations, we Muad coded a finite element solution to a Kirchhoff rod model. So basically a beam that can bend and twist with large amplitude in 3D to a wake oscillator model. So what that means is this is a phenomenological model of vortex shedding. And so when we couple both of these things together, what we see is that the vortex shedding can make the object vibrate. And so here we have the wave surge that goes back and forth at a low frequency. And so this makes the whole rod bend with the flow. And on top of that, because of the wake oscillator model, the rod vibrates in the transverse direction. And so the motion of this rod is reminiscent or similar to the branches, to each individual branches that we see on the coral colony. And so this is a qualitative confirmation that this mechanism can definitely be responsible for what we observe on the real coral. So now that we're satisfied with our elucidation of the origin of these vibrations, let's see what it means biologically. So we need to idealize our system, because a real coral colony has complex geometry, it's branching, it's 3D, it has all these lumps and polyps on its surface. So we'll make it simple. We'll just consider a cylinder, and we'll take a 2D cut of it. So basically just a circle subjected to uniform flow. And this cylinder can oscillate, it's free to vibrate with linear springs in the transverse direction and in the inline direction. And so we'll compute the trajectories of particles and see which ones get captured by the cylinder. So how we did this is we used an in-house fluid structure interaction finite element solver, which couples the fluid dynamics to the elasticity equations, to the elastic spring-mounted cylinder equations. So we solve the incompressible flow 2D. We solve the full Navier-Stokes equation with mesh deformations, and we don't use any turbulence model. So we're at fairly low Reynolds number, so we're able to resolve the smallest scales of what we see in the fluid flow. And what we do here is we make a strong assumption. So we say that in a first step, we compute the fluid flow. And then we assume that the effect of particles, because they're so small and so few in concentration, that these particles have no effect on the flow itself. So that allows us to do a first step fluid flow solution. And once this is done, we extract the fluid flow solution, and then we use it to compute particle trajectories, basically doing a sum of forces with the inertia and acceleration of the particles, their drag, the effect of flow pressure, and then the added mass of each particle. And so we release these particles upstream from the cylinder and look at which ones collide with the cylinder. And so this is how we define capture. It's basically a collision. So when our particle have a certain radius, and the cylinder has its own radius, and when we detect a collision, we declare the particle capture. So once we have this, once we can define a capture with a collision, then we can define a capture rate. So what we do is we release particles at different positions upstream, and then we seek to find the boundary between at which, if we release a particle just above this boundary, the particle will flow past the cylinder. But if we release it in between these two boundaries, then the particle will be captured. And so we find that band, that width here, where all the particles released will be captured. And so if we assume that all the particles are randomly distributed or uniformly distributed upstream with just a simple concentration, then figuring out this width here will give us the capture rate. And so that capture rate, once we define a non-dimensional version of it, dividing by the concentration and the flow speed and the cylinder diameter. And it depends on a certain number of dimensionless numbers. The mass number and the density ratio which we will both consider constant in our study. So we'll consider particles that are slightly heavier than water. That leaves us with three parameters, which we will investigate. So the diameter ratio of these particles with respect to the cylinder diameter, the Reynolds number, which is the ratio of inertia force divided by viscous forces in the flow, and then the reduced velocity, which we talked about earlier, which is based on the cylinder natural frequency and the fluid flow velocity. And so before we move on to vibrating cylinders, we start with just a fixed cylinder. So we fix the reduced velocity to 0. And then we obtain the capture rate on a fixed cylinder. And so what Moad was able to find is a nice scaling which existed in the literature, but Moad was able also to develop an analytical expression for or reasoning for this scaling. But basically, we have a 1:1 scaling between the capture rate and the radius ratio square and the Reynolds number square root. And so for small particles at low Reynolds number, we have a nice 1:1 scaling, which deviates when the particles get a little larger and the Reynolds number gets larger. And so what we see is in this range here, the viscous forces dominate and the particles are very small. Whereas in this range, inertia starts to become important as the particles get larger and the accelerations effect become much more important. And so this is why it deviates from the scale. But nevertheless, we define with these fixed cylinder a baseline, which allows us to understand better what's going on with the vibrations. So here we trace the capture rate versus the reduced velocity, and we have our baseline at a Reynolds number of 100 for a fixed cylinder. And now, if we consider the vibrations of the cylinder, what we find is that at low reduced velocity, basically the cylinder doesn't vibrate, and so its capture rate is the same as a fixed cylinder. But then there's this reduced velocity range where the capture rate is increased with respect to the baseline. And then if we go to higher reduced velocities, then the vortices are shed too fast and there's little effect on the capture rate. And so this is for a Reynolds number of 100. We can repeat this for Reynolds numbers between 50 and 200. And we see the same general trend. It's just that our fixed baseline for the fixed cylinder is different. But so if we scale all these simulations together, basically taking the subtraction of the capture rate with our fixed baseline divided by our fixed baseline, we can more or less collapse all our data points into a master curve like this, which gives us our gain in capture in percentage versus the reduced velocity. And so this is our most important result. We find that when the reduced velocity is around 5, we can get a gain in particle capture, which can reach up to 40%. So basically, a vibrating cylinder can capture 40% more particles than a fixed one. And so if it means food, 40% more food is non-negligible. And how do we explain this? Well, basically, it's our lock-in range, right? So we showed it earlier, when you have a vibrating cylinder, in the lock-in range where the vortex shedding frequency matches with the natural frequency of the cylinder, there's a great amplitude of vibrations of the cylinder. And so when the cylinder vibrates with great amplitude, it's better at capturing particles. So there's a very interesting idea here. So a biological system potentially benefits from VIV, from vortex-induced vibrations. It can capture more food. And so this is in direct contrast with what happens in engineering. In engineering, vortex-induced vibrations are a big issue, and they're up to recently, they were the only reason to study vortex-induced vibrations was to suppress them. And so if you Google, if you search for patents, you can find more than 5,000 results for vortex-induced vibration suppressions. All these strakes that you find on chimneys, on oil platforms and risers, there's all these inventions meant to suppress vortex-induced vibrations, whereas soft corals benefit from them. So this is a stark contrast. And so I want to conclude with this. Basically, this is our story. Soft corals vibrate because of vortex shedding, so they're subject to vortex-induced vibrations. These vibrations are good for particle capture. In the lock-in range, they can capture up to 40% more particles. And so if you want to read more about it, we have 2 preprints that are online. One was just accepted in Physics of Fluid. We hope that the second one appears soon. So please feel free to contact me if you have any questions with regard to this presentation.